There are discoveries that emerge silently. They don't arrive accompanied by cosmic explosions or spectacular images, but hidden in almost invisible details. A slight oscillation in the light of a distant star, a faint chemical signature lost within a spectrum, molecules slowly passing through the sensors of a telescope billions of times more sensitive than anything ever built by humanity. Small signals that, in isolation, seem insignificant, but which, together, can forever change the way we see our place in the universe. And now, for the first time in decades of searching, scientists believe they are facing something that goes beyond the simple search for extraterrestrial life. Perhaps we are beginning to observe real evidence of a world that could be alive at this very moment. About 40 light-years from Earth, orbiting an ancient, cool, and compact red dwarf star, lies a planet called TRAPPIST-1e, a rocky world located precisely in the habitable zone of its star, the narrow band where temperatures could allow for the existence of liquid water on the surface. For years, it was treated as just another promising candidate among thousands of exoplanets discovered. But everything changed when the James Webb Space Telescope began analyzing its atmosphere with a level of precision that astronomy had never achieved before. The data revealed is as delicate as it is disturbing. Layer after layer of spectral signatures began to indicate the presence of conditions that strikingly resemble Earth's own environment. Not just any rocky planet, but a world that may possess a stable atmosphere, complex chemical balance, and even the possibility of oceans persisting under a sky eternally illuminated by a gigantic red star on the horizon. And that's exactly what's putting the scientific community on alert. Because, for the first time, we may be looking at a planet that brings together virtually all the fundamental ingredients to sustain life. A place where chemical reactions could evolve over billions of years, where liquid water may exist permanently, and where the line between a habitable planet and an inhabited planet is slowly beginning to disappear. Today, we'll explore why TRAPPIST-1e has captured the imagination of astronomers worldwide, how the James Webb Space Telescope was pushed to its limits to detect its atmosphere, and what the evidence really means for the possibility of life beyond our solar system. When scientists first pointed their telescopes at the faint red ember known as TRAPPIST-1, nobody expected much. A nearly dim M8-class red dwarf, emitting only about 1,800th of the luminosity of our Sun, cold, ancient, and seemingly unremarkable. But behind its tranquil appearance lay a true cosmic lottery, unlike anything ever discovered before. One by one, astronomers detected small dips in its light, signs of planets passing in front of the star, and soon realized they weren't looking at just one habitable candidate, or even just a few. They had found an entire family of Earth-sized worlds, 7 rocky planets orbiting closer to their star than Mercury orbits the Sun, locked in a gravitational embrace so intense that the same side of each planet is always facing the star. Initially, many experts dismissed the system as hostile. Red dwarfs are known for extreme explosions, violent magnetic storms, and chaotic radiation capable of destroying atmospheres before life even has a chance to emerge. But TRAPPIST-1 refused to be dismissed. Its orbit positions TRAPPIST-1e precisely in the heart of the star's habitable zone, receiving approximately 2/3 of the light that Earth receives, an amount that could be sufficient to sustain liquid water, provided the planet manages to maintain a stable atmosphere. And it was precisely this question that became the focus of one of the most important exoplanet observation campaigns in history. Because TRAPPIST-1e is not just another rocky planet. It is considered the most promising candidate ever discovered to resemble Earth around another star. When NASA released priority observing time for the James Webb Space Telescope, one of the teams with guaranteed access, the DREAMS collaboration, made an immediate decision to point the world's most advanced telescope directly at TRAPPIST-1e. The goal was both simple and extremely ambitious: to discover whether this small, distant world actually possessed an atmosphere. To do this, scientists turned to transmission spectroscopy, an incredibly sensitive technique that measures how a planet's atmosphere absorbs tiny fractions of starlight during a transit. For most exoplanets, this type of analysis is nearly impossible. But TRAPPIST-1 offered a rare advantage. Because the star is extremely faint, any planet crossing in front of it blocks an unusually large portion of its light, producing a much more intense signal than that observed in stars similar to the Sun. Webb's NIRSpec instrument recorded the wavelengths absorbed during 4 different transits of TRAPPIST-1e, and the initial results immediately ruled out several hypotheses. The planet does not possess a primordial atmosphere rich in hydrogen and helium. Radiation from the red dwarf would have destroyed that billions of years ago. It also does not have a dense, suffocating atmosphere dominated by carbon dioxide like Venus, nor an extremely thin and decaying atmosphere like Mars. These possibilities were ruled out. What remained was something far more intriguing: the chance that TRAPPIST-1e possesses an atmosphere similar to Earth's, dominated by nitrogen, with greenhouse gases such as water vapor, methane, or carbon dioxide in smaller concentrations, but sufficient to sustain habitable conditions. And if this atmosphere exists with a pressure close to 1 bar, similar to Earth's, it could transport heat to the dark side of the gravitationally locked planet, allowing for the existence of a global ocean under a sky eternally divided between perpetual light and endless darkness. It was at this point that some scientists began to suggest, discreetly and cautiously, that perhaps this world was more than just habitable. Perhaps he was alive. But the presence of an atmosphere, by itself, does not mean life. Because it is so close to its star, TRAPPIST-1e is likely tidally locked, meaning one side remains in constant light while the other is plunged into a freezing night. The big question became whether this planet could redistribute heat efficiently enough to avoid catastrophic climate extremes. Webb data provided important clues, but not yet definitive answers. If the atmosphere is dominated by methane, the greenhouse effect could work in reverse, cooling the surface and limiting liquid water to only the sunlit side. Instead of a global ocean, TRAPPIST-1e might possess a vast sea restricted to a single hemisphere, an environment where prebiotic chemistry could thrive in heated pools under a reddish-orange sky. Some simulations have even shown that life could survive along the so-called Terminator line, the narrow band of eternal twilight that separates day from night, a climatically stable region known as Terminator habitability. Other researchers propose an even more extreme scenario: TRAPPIST-1e as a frozen volcanic world with a subsurface ocean, similar to Europa and Enceladus. On such a planet, hydrothermal vents could function as cradles for emergent organisms, just as many scientists believe happened on early Earth. Regardless of which of these hypotheses is correct, the implications remain profound. TRAPPIST-1e may not be a simple copy of Earth. It could be something stranger, more alien, more diverse, and yet perfectly capable of sustaining life. And the chemistry detected by Webb only deepens the mystery, rather than solving it. Of all the factors that shape the chances of life on TRAPPIST-1e, none is more dangerous or more essential than the star it orbits. TRAPPIST-1 is a volatile red dwarf, whose flares surpass anything produced by our Sun. The most intense geomagnetic storm ever recorded in Earth's history, the Carrington event, would be a routine occurrence on TRAPPIST-1e, happening on average every 2 days. These storms release torrents of radiation capable of stripping away atmospheres molecule by molecule, potentially turning worlds into barren rocks even after oceans have formed and life has emerged. But paradoxically, these same explosions may be necessary for the origin of life. Ultraviolet radiation plays a fundamental role in the formation of the chemical building blocks of RNA, the fundamental molecules behind all known organisms. Today, TRAPPIST-1 is much calmer than in its violent youth, offering a possible window for life to emerge and be sustained, provided the planet possesses some form of protection. And TRAPPIST-1e may indeed have that protection. A molten iron core could generate a magnetic field strong enough to protect the atmosphere, especially with tidal forces constantly compressing the planet's interior and generating heat, similar to what happens with Io, Jupiter's moon, shaped into permanent volcanic activity by gravitational stretching. Combine a magnetic field, an atmosphere, an efficient heat distribution system, and the possible presence of water, and suddenly, the odds begin to favor a world that is not only habitable but surprisingly resilient. Still, Webb's data cannot definitively confirm the truth. TRAPPIST-1e could be a vibrant ocean world or a frozen, airless sphere, doomed before it even had a chance. What Webb confirmed, however, is that this world is unlike any other we have studied before, and that its probability of sustaining life, based on all known metrics, makes it the most promising candidate humanity has ever encountered. If TRAPPIST-1e truly possesses an atmosphere, its mere existence would be a small miracle. Because although TRAPPIST-1 is a faint and old star, it is also a red dwarf, one of the most temperamental stellar classes in the galaxy. Red dwarfs erupt with ferocious explosions, powerful magnetic storms strong enough to surpass anything ever produced by our Sun. In fact, it is estimated that the worst geomagnetic event in Earth's history, the Carrington event, occurs on TRAPPIST-1 every 2 days, a terrifying rate of destruction that would bombard any nearby planet with torrents of charged particles. And if TRAPPIST-1e orbits so close that its star appears 4 times larger in the sky than the Sun appears from Earth, then its atmosphere must withstand a cosmic onslaught virtually in real time. This raises an inevitable question. How does a world survive such fury long enough for life to emerge? Red dwarfs have extremely long lifespans. TRAPPIST-1 will continue to shine for about 10 trillion years, much longer than the current age of the universe itself. But these tranquil billions of years only come after a violent and destructive youth. If TRAPPIST-1e attempted to form a secondary atmosphere during this chaotic phase, the star may have destroyed it before it even matured, leaving the planet airless and sterile. And yet, the ambiguous signals from James Webb suggest that something different may be happening. Because if TRAPPIST-1e still possesses an atmosphere, then it survived odds that should have wiped it out billions of years ago. This, in itself, would raise the probability of life far beyond mere chance. Survival itself becomes self-evident. Even if the surface of TRAPPIST-1e is cold or partially frozen, the planet may hide a secret advantage deep beneath its crust: tidal heating. Because of its close and possibly eccentric orbit, TRAPPIST-1e is constantly stretched and compressed by the gravitational pull of its neighbors in the 7-planet system. This continuous deformation injects heat into the planet's interior, heat that can fuel volcanism, magnetic activity, and even subsurface oceans. The paper compares this phenomenon to Jupiter's moon Io, the most volcanically active body in our solar system, a world whose interior is energized simply by the gravitational tides caused by its neighboring moons. TRAPPIST-1e may experiment with a similar mechanism, generating about 18 watts per square meter of internal heating, 24 times more than Earth receives from tidal forces. This is not just a geological curiosity. Internal heat can keep liquid water under an ice sheet, drive chemical reactions, and sustain entire ecosystems without sunlight, much like hydrothermal vents sustain life in the deepest regions of Earth's oceans. If TRAPPIST-1e has volcanic activity, it could continuously replenish atmospheric gases such as carbon dioxide, methane, or nitrogen, exactly the gases that James Webb is trying to detect. Tidal heating could therefore be the planet's heartbeat, a hidden engine that keeps it alive even when starlight fails. There is a strange paradox at the heart of TRAPPIST-1e, a contradiction that may determine its fate. The intense stellar explosion activity of TRAPPIST-1 could easily destroy atmospheres and sterilize surfaces. However, this same radiation is also considered essential for the creation of life. On Earth, ultraviolet light played a fundamental role in the formation of the chemical building blocks of RNA, the molecules that allowed the first life forms to metabolize, grow, and reproduce. In other words, without a certain level of stellar violence, life as we know it might never have arisen. TRAPPIST-1 may be exactly at the point of equilibrium between these two forces, a narrow boundary between destruction and creation. Red dwarfs eventually calm down, entering long stable phases with much lower emission of ultraviolet radiation and X-rays. TRAPPIST-1 is now in this phase, which means that the planet may finally have the stability necessary for life to persist. But the question remains, did the atmosphere survive long enough to benefit from this calmer era? The document suggests a promising possibility. If TRAPPIST-1e developed a magnetic field comparable to Earth's, generated by a molten iron core and strengthened by gravitational tidal energy, it could have protected its atmosphere for billions of years. This would place TRAPPIST-1e in a rare category of worlds that survived the worst and emerged as stable planets capable of supporting life. A world shaped by violence, but not destroyed by it. A world forged in extremes that may have unintentionally created the perfect conditions for the emergence of biology. The James Webb Space Telescope delivered the first clues to the atmospheric composition of TRAPPIST-1e, but the document makes it clear, the real discovery has not yet happened. Scientists have already scheduled 15 additional transits before December, each allowing Webb to collect more precise spectral data, refine the molecular signatures of the planet's atmosphere, and increasingly reduce measurement noise until doubt finally gives way to certainty. These transits are no ordinary observations. They represent the most ambitious campaign ever undertaken to characterize the atmosphere of a rocky exoplanet orbiting a red dwarf. If Webb detects carbon dioxide, methane, or nitrogen with consistent signatures, this will confirm the existence of a secondary atmosphere, a monumental advance in assessing the planet's habitability. If water vapor is found, even in minute quantities, the consequences could be historic. And if the spectral patterns match those of a stable atmosphere similar to Earth's, then TRAPPIST-1e will become the most compelling candidate for life ever identified. But the tension surrounding this world isn't just scientific. With each new observed transit, the suspense only intensifies. Will this planet be revealed as a frozen, lifeless sphere, or as an active world with complex climates, oceans, advanced chemistry, and perhaps even biology evolving beneath a dark red sky? Humanity may be just months away from the first real confirmation of life beyond Earth, or the painful realization that we've come incredibly close, but still not close enough. In any case, TRAPPIST-1e ceased to be just a distant planet. It became a mirror pointed directly at the deepest question of our existence. Are we alone? One of the most impressive and also most unsettling aspects of this system is the colossal age and incredible longevity of its star. Red dwarfs are the true slow burners of the universe, consuming fuel so gradually that their existence can reach 10 trillion years, a number so gigantic that it makes the current age of the universe, about 13,800,000,000 years, seem almost irrelevant. TRAPPIST-1e has already survived the most violent phase of its star, a chaotic period in which extreme explosions could have destroyed atmospheres, sterilized entire surfaces, and completely reshaped the planetary system. But this same extraordinary longevity means that planets like TRAPPIST-1e could, in theory, sustain life for billions and billions of years, far beyond the time Earth will ever have available. Even if the planet lost its first atmosphere in the early stages, the time available for regeneration, geological recycling, and atmospheric reconstruction would be virtually unimaginable. This transforms TRAPPIST-1e into a world where life, if it truly arose, would have had more time than any terrestrial organism could dream of to evolve complexity, intelligence, or even completely alien biological systems. The paradox is unsettling. TRAPPIST-1's greatest threat to life is lost in the distant past, but its greatest gift is precisely the near-eternal stability that followed. And TRAPPIST-1e remains right at the center of this unimaginable temporal ocean. Among the most fascinating details of the document is the subtlety of the James Webb spectral readings, data so sensitive that scientists need to interpret them with extreme care. The first transit spectra of TRAPPIST-1e show neither the deep signatures of a thick carbon dioxide atmosphere nor the clear markers of a primordial hydrogen envelope. Instead, they reveal a weak and ambiguous pattern, a spectral silence, that can only be explained by two possibilities. Either the planet truly has no atmosphere, or it has a dense, compact atmosphere dominated by molecules heavier than Webb molecules. It is only just beginning to detect it, even from 40 light-years away. And it is precisely this ambiguity that makes TRAPPIST-1e so fascinating. A nitrogen-rich atmosphere, like Earth's, would leave an extremely subtle signature during the transit, something that requires multiple consecutive observations to be reliably identified. And that's exactly what scientists are racing to achieve. This situation is unlike any previous discovery of exoplanets. It is not a triumphant identification of methane or water vapor, nor a clear declaration of atmospheric collapse. It's like a scientific thriller, data balanced on a razor's edge, where each new observation can completely change the interpretation to a living, pulsating world or to a silent, frozen planet. The fact that the readings from TRAPPIST-1e remain so difficult to classify may, in itself, be the strongest indication yet that its atmosphere is similar to Earth's, and not something exotic or extreme. One of the most fascinating concepts raised by the gravitational locking of TRAPPIST-1e is the possibility of a terminator habitat, a ring-shaped region of permanent twilight where conditions could be ideal for life. On the illuminated side, temperatures could soar beneath the stationary red star, causing intense heating and possible evaporation. On the night side, darkness stretches on forever, cold enough to freeze entire oceans. But between these two extremes lies a thin, dynamic boundary where the star's heat meets the cold of the deep night, creating a stable zone with temperate conditions similar to Earth's. In this zone of perpetual twilight, winds circulating between the hemispheres could maintain a stable climate, capable of sustaining liquid water and moderate temperatures. The document highlights that, in several climate models, even a limited atmosphere or a small amount of water would be sufficient to generate long-term stability precisely along this dividing line. Life in such a region would evolve in an environment completely different from anything existing on Earth. Neither light nor dark, but a world permanently bathed in a reddish-orange twilight. Plants, if they existed, would likely adapt to the low light levels. Animals could evolve to navigate temperature and light gradients rather than day-night cycles. TRAPPIST-1e may not harbor a complete planetary biosphere, but rather a narrow habitable zone, a cosmic equator, where life clings to balance in a world perfectly divided in half. Although much of the enthusiasm surrounding TRAPPIST-1e is focused on its potential surface conditions, the paper also opens up the possibility of a completely different type of habitability, a subsurface ocean, similar to those of Europa or Enceladus. If TRAPPIST-1e is a volcanically active world, with tidal heating pushing molten rock upwards and fracturing the crust, it could easily support pockets of liquid water beneath layers of ice. On Earth, life thrives in this kind of darkness, feeding on chemical gradients rather than sunlight, and some scientists believe that life may have originated precisely in hydrothermal vents in the deep ocean. TRAPPIST-1e may reflect this same environment, with volcanic fissures releasing mineral-rich fluids into an ocean sealed beneath kilometers of ice. What makes this scenario so fascinating is that subsurface oceans are naturally protected against atmospheric loss, stellar explosions, and extreme radiation. Even though TRAPPIST-1e lost its surface atmosphere billions of years ago, a vibrant biosphere could still exist below the surface, completely isolated from stellar violence. This completely transforms the search for life. Instead of just looking for spectral signatures of gases, perhaps in the future we will need instruments capable of detecting geothermal activity or cryovolcanic plumes. TRAPPIST-1e may therefore be a world where life survives, not because conditions are mild, but because it has retreated to a protected sanctuary beneath the surface, waiting for us to discover it one day. Ultimately, TRAPPIST-1e stands out as one of the most extraordinary worlds ever discovered by humanity, not because it guarantees the existence of life, but because it refuses to let the question die. Each measurement, each spectral line, and each transit observed by the James Webb Telescope draws us even deeper into a mystery that becomes more intriguing with each new set of data analyzed. A world trapped in permanent extremes, half consumed by eternal light, half plunged into endless night. And yet, perhaps it will find ways to remain habitable through dense atmospheres, hidden oceans, or heat generated by tidal forces. A planet orbiting a star so ancient and enduring that it makes the entire history of Earth seem like a fleeting instant. A world that survived the violent youth of a red dwarf, withstood storms capable of destroying entire atmospheres, and now exists in a delicate equilibrium where life could emerge in regions of eternal twilight, subterranean volcanic oceans, or even global seas warmed by an invisible greenhouse effect. What the James Webb Space Telescope has revealed so far is not a definitive confirmation. It's a possibility. A possibility so strong, so statistically impressive, that TRAPPIST-1e now occupies the center of the search for life beyond Earth. The absence of hydrogen, the exclusion of a Venus-like atmosphere rich in carbon dioxide, the signs of heavier gases, and climate models that indicate stability even in gravitational lockup, all point to a planet that may have managed to defy cosmic odds. And yet, the risks remain. Violent explosions of red dwarfs capable of stripping away an entire atmosphere, gravitational forces that could fracture the planet's interior, and timescales so vast that life might arise and disappear before we can even detect it. TRAPPIST-1e could be a vibrant, bustling world, or a silent graveyard lost in space, a living planet shaped by eternal twilight, or just a frozen, atmosphereless sphere. But that's precisely what makes it all so extraordinary. For the first time in history, we are not just looking at vague clues, distant gas giants, or theoretical models without any observational confirmation. We are observing a real world, a rocky planet the size of Earth, located 40 light-years away, whose atmosphere may finally be within reach of our scientific confirmation. A planet where chemical reactions may be happening right now under crimson skies. A planet that may be writing its own version of life right now. And with 15 more James Webb transits already scheduled, the answer is drawing closer, slowly, silently, inevitably. Perhaps TRAPPIST-1e will disappoint us. Perhaps its surface is cold, barren, and without an atmosphere. Or perhaps, just perhaps, It will become the first world in human history that we can point to and say, life exists there. And when that moment arrives, everything changes. Our science, our future, our vision of the universe, and of ourselves. If you want to follow these discoveries in real time, see every new update from the James Webb Space Telescope, every advance in atmospheric analysis, and every new clue about this extraordinary world, don't forget to subscribe, turn on notifications, and stay with us. Because we are closer than ever to answering humanity's oldest question, and the next piece of this truth could emerge at any moment.